All right, so we're going to be learning about conservation of momentum in this video. Conservation of momentum is very similar to the conservation of energy that we've already done, in that if we have a closed system, then the total amount of energy or of momentum before whatever happens is the same as the momentum that exists after whatever happens. Often it's a collision, and you're going to really want to watch for that keyword collision because that always signifies that it's a conservation of momentum problem. But whatever happens, momentum is always conserved. And momentum, as we'll learn in this unit, is actually conserved kind of more consistently, or we can use conservation of momentum a lot more often than we can use conservation of energy. It's a very, very useful concept. The only times that we can't really use conservation of momentum, and I want to be particular or specific here, momentum is always conserved. We just can't always use it. The times that we can't use it is when we can't define variables for objects involved in the collision. So for example, if I had two carts crash into each other, there's a pretty good chance that I can describe the velocity of the objects before and after. I had like a slow motion camera and some meter sticks and some timers and stuff. I could figure out all that stuff pretty easy. On the other hand, if I drop a ball or I drop a brick or something and it hits the ground, whether it bounces or stays still, I can't do a very good job of figuring out the conservation of momentum for that system because the Earth is part of it, and measuring the change in velocity of the Earth would be nearly impossible because it's so small. So just keep in mind that conservation of momentum is always true, but you generally need to have the ability to look at the velocities and masses of both objects in order to use it in a problem. This is an example problem that I have right here. I have mass A and mass B. They're coming towards each other. Mass A has a mass of 2 kilograms and it's going at 2 meters per second. Mass B has a mass of 4 kilograms and it's going at 1 meter per second. And so the question is, like, what happens in this particular scenario? So I'm going to put in some more numbers here. I want to put in the velocities into my little table here. And one of the big things, the big mistakes that I'll talk about a lot in this unit is making sure that you pay attention to the signs of your velocity and to your momentum. When we talked in kinematics about picking a coordinate system and making sure that we define everything that way, it was important in kinematics. It is critical here. If you mess it up in kinematics, a lot of the time you can kind of catch your mistake and just like quietly turn a plus into or a minus into a plus. If you mess it up in conservation of momentum, you're going to get totally the wrong answer. And odds are the wrong answer that you get will be on the list of possible answers because they know students mess that up so frequently. So be careful. In this problem, since I said going to the right is positive, block A or cart A has a velocity of 2 meters per second, and block B or cart B has a velocity of -1 meter per second because it's going the opposite direction. So one way that I can diagram this and look at these is I can do it by drawing a momentum diagram or momentum bar charts that are really similar to the energy bar charts we used in our last unit. For these bar charts, I'm going to do anything along this axis as my mass and anything along that axis as my velocities. So for example, mass A has a mass of 2 kilograms, so that's why I'm going 2 over, and a velocity of 2 meters per second. So if I was trying to describe this mass, it goes over 2m, or 2 kilograms, whatever, and it goes up 2 meters per second. So there's this momentum, and if we multiply this, if we find the area of this particular doohickey, it's 4 kilogram meters per second. Doohickey is the official scientific word. I'm gonna write that below because it's a little bit hard to see there. 4 kilogram meter per second. For the other one, for mass B, it is 4 units of mass. So that's going over 4 kilograms. But it has a speed of -1. So I'm going down 1 instead. That's -1 kilogram meters per second. So the total momentum here is going to be -4 kilogram meters per second. So if I figure out the total momentum for this system, this is the sum of the momentum, is 0 kilogram meters per second. That means no matter what happens in this scenario, at the end, after the collision takes place, we still have to have 0 kilogram meters per second. The only way that would be not true is that there was some outside force acting on it. Like, for example, if this whole thing was set at a slant so that there was an outside force of gravity, it would seem as if momentum had increased because we have this outside force acting on our system. Okay, so going from there, let's talk about what happens here, or really we're going to talk about some possibilities. We have some possibilities of what could happen. I'm going to give 3 of them. Option 1, they both stop. If they both stopped, then mass A would have a velocity of 0, and mass B would have a velocity of 0, and you can see that the total area there would be 0. So that's one option, that they just smack into each other and they both stop each other. You can imagine this kind of being like 2 toddlers running. They're running and then they just smack into each other and they fall. The next option, the next thing that could happen, is that maybe mass A bounces off and starts heading the other direction. So it could go something like this. It just bounces right off. Now it's still 2 mass units, but now it's going the opposite direction, so -2 velocity units. And then mass A does something like this, where it now bounces off going the other direction with 4 kilogram meters per second, going in the positive direction versus the -4 kilogram meters per second in that direction. That still has a total momentum of 0, so it still works from a momentum perspective. Our last option is maybe somewhere between those two. Maybe mass A bounces off, but it's only going back by 1 unit, so it has a momentum of -2 kilogram meters per second. And mass B is going to keep going forward, but not very fast at all. So it still has to be 4 over because it's the same mass, but it's only 1/2 velocity unit. So that's still 2 total. So all of these still work, and there's basically, with the information I've given you, an infinite number of possibilities because all of these do their job of conserving the momentum before and after. Exactly what happens has to do with how the carts are constructed, and there's some more information when we learn about types of collisions that will help us kind of figure out the information there. So moving on to the next problem, this got a little bit uglier than I meant. Let's kind of section it off right there. This conservation of momentum also works in 2-dimensional problems. And if you saw a 2-dimensional problem on the AP exam, it would probably look something like this. Like we have right here, our initial object that's moving at 5 meters per second due right, or due left. Directions are hard. So it's going 5 meters per second to the left. And then something happens. That's what that box is. It's like something happens. They draw the box there to be like, you don't see what happens. You just know that like it hits an object in some way. And after that collision, we know that this object here is moving off in this direction. Actually, it works out to be exactly 5 meters per second. And it wants to say, it says that's actually a new object. Maybe they're 2 different colored marbles. So we knew that we had a black marble going in, but on the way out, we have a really, 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 really dark gray marble. And then what is the black marble now doing? So that would be the question that you're asked. And one thing to realize right now is that momentum was not conserved here. Just because we have the same speed going in and the same speed going out doesn't mean that momentum is conserved. Momentum is a vector quantity. So given that we had 5 meters per second times whatever the mass of the marble is at the beginning, we need to have 5 meters per second coming out of it on this side. A total of 5 kilogram meters per second coming out on that side. We only have 4 based on the drawing that I gave there. We also have it moving down now, and we have to somehow explain how it's moving down, even though at the beginning it had 0 vertical momentum. So this one I would actually solve graphically. We can see that we need to add 1 unit of horizontal motion, or 1 meter per second horizontally, and then we have to add 3 vertically to offset the -3 that very, very dark gray one is. So that means that the other object would have a momentum that looks like that. And I don't know exactly what that is. The magnitude of it would be the square root of 10. Um, but I don't know. You can figure out the angles on your own if you really care that much. So that's the idea, though. That we need to have the momentum before equal to the momentum after, and this works similar to projectile motion, that horizontal momentum and vertical momentum have to be conserved separately. So there you go. There's conservation of momentum in some simple examples, and then we'll hit some more complicated things in class and in the other videos. Thank you very much for watching.